Okay, so today we're actually going to be focusing how the notion of continuity will actually help us evaluate limits in an algebraic fashion. So last time we talked about how a function was continuous at a point. This is the same definition that we used last time. If the value of the function, the limit is the same as the value of the function. And the one thing that's useful here is it's basically saying that as long as you have a continuous function, you can calculate this limit here by just evaluating the function, by basically plugging in. Because how do you evaluate functions? You just plug in. So the idea is if you plug the function and you know that it's continuous, you can immediately find the limit. So that is to say that the limits of continuous functions can be evaluated just by direct substitution. That is, it's the same way that you evaluate functions. Even though limits and evaluation of functions are not the same thing in general, with the continuous function, they are the same thing. So that becomes very, very useful. So the natural question we should ask is, are there any functions that, at least, again, in an introductory calculus class, we will just automatically assume without proof that they are continuous. And I guess we could rigorously prove it. But again, usually that's a more advanced topic. But if we just take them as continuous, what are those functions? And I figured a good idea would be just to simply make a table here and go down the list of common functions that are continuous. Okay, so a polynomial, for example, is going to be continuous everywhere. So again, what is a polynomial? It's any type of function, and there is a couple key things, though, that are important. One is that there needs to be a finite number of terms. You can't have an infinite number of terms. The second thing is that we only have positive powers of x. So you can't have something like x to the negative third. Although, as we'll see going forward, in many cases that, well, depending on the problem, it shouldn't be necessarily too big of a deal. Rational functions are going to be continuous on their domains. So what does that mean? That means as long as the function is defined, that means you're not dividing by zero, it will be continuous, and you can just evaluate the limit by direct substitution. So that's what we mean by on the domain. Okay, so again, if you're dividing by zero, that doesn't count, but as long as you're not dividing by zero, that's going to be fine. Roots are also root functions, anything x to the 1 over n, that's going to also be something that's continuous on the domain. Again, taking square roots of negative numbers will give you a complex number, and we don't want complex numbers here. So that would be something that where it wouldn't be the domain. So again, remember the domain is everything where it is defined, not the places where it's undefined. Exponential functions, of course, are continuous on all reals. So anytime we have an exponential, that's good. Logs on the domain, trig functions on the domain. Again, sine and cosine, their domain is all reals, but again, keep in mind, you deal with things like tangent of x, and tangent of x has a whole bunch of vertical asymptotes. So you just have to be careful that you have to make sure that we're talking on the places where it is defined. And also inverse trig functions will be continuous on their domain. And then it turns out that as long as the conditions are met, that you have a defined function, if you take a sum, difference, product, quotient, exponent, or root of any of these, and they're also going to be continuous on their domain. So in many cases, although not all cases, you can simply, the idea is if you evaluate by direct substitution, then if you get a real number out, most of the time it's going to be the value of the limit. Okay, so just to indicate, and I think it'll make more sense when we do this, but if I do direct sub and I get a value, so I'm not dividing by zero, it's not undefined, that's usually going to be the limit. Again, sometimes, with piecewise functions, that oftentimes won't be the case, but in many other cases it will. So what does this actually look like? Well, let's look at a couple examples, and then we'll also show an example here where it doesn't work. So if I want to figure out what this limit is, this is a polynomial. I don't have to look at values to the left of 1 and to the right of 1. I can simply just plug in 1 for x, and we can figure this out. So that's going to be 3 plus 5. Actually, I can't do math in my head. 3 plus 2, that's 5, minus 4, that's 1. So that's all you got to do. Really simple. Let's say we have something like this. So again, this is an exponential. We've got a square root function. Again, if we get something that is defined, then that will be the limit. So let's try this. So this is going to be 1 half in the numerator. Then that's the square root of 4, which is 2. So this will yield 1/4. So again, we get a number that's good. Again, both of these are the limits. But let's take this last example, because you get in the habit of doing substitution. Hey, that's going to work out. So we're going to plug in 1, and then we're going to plug in 1, and well, what do we get? Oh, we get 0 over 0, and this is undefined. Okay. Now, does that mean that the limit is undefined? Not necessarily. Okay, so we actually need to do more to find the limit. And I think we'll probably come back to this. If I'm not mistaken, I think the value of the limit is actually going to be equal to 2. But when you do substitution, the key thing to note is that if you get a real number out of the other side, again, not always, there might be some, again, piecewise functions where you have to be a little bit more careful, but if you get a real number out, that's usually going to be the answer, especially when you're dealing with normal looking functions, polynomials, rational functions with square roots in them. If you get something that's undefined, we have to stop and we have to figure out what to do. And I don't know if we're going to talk about how to deal with this next time, but pretty shortly we'll be dealing with ones where we'll give you something like this, and we'll look at the different techniques that you can use in order to actually figure out what that limit is. So that'll be later, but this is our first algebraic tool to evaluate limits. So as always, I hope this helps, and as always, take care.